bad for whoever is going to play it because my friend is like, he's really, really, really good. So I kind of feel bad for whoever had got to be the organist for that wedding because there's no way they were going to be as good as him, but they could try.
I said after the wedding, and once like they had to stop the party and stuff after the something. They went back to my grandparents' room and kept partying
Oh my gosh, did they really?
till 3 in the morning.
Wow, they were having a good old time, huh?
Yep.
That's funny.
I left to go to the pool with one of my far cousins.
Mm-hmm.
And
So I remember
I left at 9.
when my aunt
They
and uncle.
stopped at 12 and kept partying till 3.
Oh, okay, there you go. I remember when I was probably a little older than you when my uncle got married and sorry, this pollen has been killing me. But
It's not affecting me.
oh, that's awful. But anyway, he got married in Greenville, South Carolina, which is where he ended up living with his wife for many, many years. Because her family's from around there. So anyway, I was a flower girl and we went to get our hair done. My other cousin Molly, who's a year and a half younger, she and I were really close growing up. We went to go get our hair done to go be flower girls. And my cousin Molly's hair was about maybe a little shorter than yours is right now, but thick. Like you have thick hair, hers is like another half or twice as thick. It's really thick.
You sure?
Her ponytail's like that. It's like that big around and she makes it, yeah, it was even thicker than yours, which is saying something because you got nice hair. So her ponytail's like this, right? She has crazy thick hair. So, and it's straight, just stick straight, just really thick. So we were at this hairdresser and she was our future aunt, my husband's soon to be, my uncle's soon to be wife had said, okay, I want them in French braids. And I want you to tuck little baby spread flowers in their braids and whatever. So it's very cute. And my cousin's mom had made us dresses, little flower girl dresses. They were like powder blue and they were really cute. So we're sitting there and this lady braids my hair. It's a French braid all the way down, done. The lady that was doing my cousin's hair was in tears because she could not get it all into a braid. It was so thick. And she tried like 4 or 5 times and she ended up crying. And then the lady that did my hair said, forget it, she's getting 2 braids. So my cousin got 2 French braids, one on each side like that, parted down the middle, and it looked so much cuter than mine. Well, then I was annoyed because she had the cute braids and I had the one braid and I didn't even like how it looked, but hey, they just couldn't do it. Her hair was too thick, just way too thick. But yeah, that was fun.
The same thing for my cousin's wedding. I was her flower girl because I was the kiddish age.
Drew got to be a ring bearer when another one of my cousins got married. Cole handed out brochure or bulletins or whatever wedding programs. And then Drew got to be a ring bearer.
These really pretty blue shoes.
Oh yeah.
And like right here, there was like a little moon.
Oh, that's cool.
And then like there was like a little blue bow right.
Oh, how cute is that?
And then the dress was like this nice satin.
I'm trying to picture you in a dress because you're always kind of tomboyish how you dress.
I don't like it matching with all the groomsmen and everything. So I just went.
Did you like it?
It was not. It was nice.
I like dresses, but
And
I'm kind of tomboyish, but I like dresses because they're comfortable to me.
nice little basket for rose.
Yes, for the pet flowers, yes.
And my cousin's wedding dress was beautiful.
Oh, yeah.
Her veil was almost as long as the dress.
Oh, I love that. That's
And
great.
At the end of the veil, like at the end, there was a little hidden V, which was her new
name,
her new last name.
That's cool.
Pretty sure it was like Manchas or something.
Okay. So a little V. That's nice. Paying tribute. I like
And
that.
she had a Big flowy.
Oh, that is cool. I had a very big dress, a poof, big dress. And it was funny, my mother-in-law, when she saw it, she said, wow, that looks really heavy. Like thinking like I had maybe not made a good decision because it was so thick and so heavy. And I was like, yeah, but I love it. What's that?
Exciting news.
What?
I drove here
By yourself?
with my mom in the car, but yeah,
So, good girl.
I almost died
When did you get your permit?
last year.
Oh, okay, so it's just the first time you've driven here.
Yeah,
Awesome.
I'm getting used to driving.
Yes, good. Let me tell you, it's gonna be a whole new world when you're on the road. You'll love it.
Great.
Good girl. I love it. I'm gonna probably have to send Drew to the gym by himself either tomorrow or Saturday. Which means he has to drive to Marietta by himself, which is the farthest he will have gone by himself. He did drive back from Florida, when we went to Florida. He drove back the whole way back, but I was in the car with him and so was his coach. It's kind of funny. Said to his coach, is this the furthest you've ever had a student drive, an athlete drive you? And he said, this is the only time I've had an athlete drive me.
During the cousin's wedding, the spot where we had to get ready and put our makeup on
Yeah,
was not as big as that closet.
ooh,
And there were 4 of us.
wow,
Young women and 1 small child.
that's not fun. All squashed in like that.
Well, it was nice. It was kind of bigger. And then the men had the entire venue. They had
Oh.
the entire venue.
Oh,
Just like that little tiny bitty closet.
you made it work though. You made it work. What's up, Eunice? How goes it, my friend?
Good.
Yeah, that's for later. Can't touch it. That's for your mystery lab. I'm sorry.
That's nuclear newts.
Yep.
Where's the 6 rats in a trench coat? Where's the
You guys are gonna be in the pub. 6 raccoons in a trench coat is gonna be in the pub. Close enough's in here, Jolly Crew's in the dining room, the nuclear newts are in this room.
Chili crew?
James's Jolly Crew,
Nuclear newts are like here.
right here. Yep, you guys will be right here. It's going to be a fun lab. I like this lab. It's really kind of
Is
cool.
there a back page on that?
There's a whole packet there. Yeah. You
You
get it.
should cover.
Yeah, you can't see what it is until you get started. It's fun though. It's a fun lab. I like it. And then the next lab that we do in our we have a week off, right? And then we have a week on, then we have a week off. On that week on is, we're gonna make our own bouncy balls.
You're gonna make a bouncy ball?
Yep, you're gonna make your own bouncy ball.
Can't you make it with the rubber? Can't you just like make it with the rubber?
You're gonna make the compound, that you're gonna make the like rubbery stuff, the polymer.
Oh,
Yep,
that's, do you get to keep it?
yes, you get to keep it, your own bouncy
So
ball.
all of us get to make one?
Yep, everybody gets to make one, everybody gets to
Oh,
do
like,
one.
I'm
like
gonna
the,
customize
like the
mine.
rocket one, the soaring.
Yes,
straw.
like the straws, yes, everybody gets to take home their bouncy ball, it will be fun. It depends on how good you are at making it round.
Like,
Oh,
Yeah, it should be fun, they're fun.
I'm gonna decorate mine.
There you go, you absolutely can if you want.
I decorate everything.
yeah, I've got the work side of you.
You got it done? Well, I love it, love that you guys are ahead of the
I
game.
use easy bib.
Pardon me, I'm still coughing a little bit from last week's mess. All the allergies and stuff and just lingering and just making me cough, but it's just
Last
annoying.
week was a disaster for lab rats. They
Mhm.
made a whole mess.
Yeah, it did. There's my girls, what's up, ladies? Hello, Emerson. Aha, AC/DC today, Good choice. What?
I'm not a rock person.
You've not been disowned from your family yet? Your dad hasn't kicked you out of the house? Isn't your dad a fan of that? Isn't he a fan of that? Yeah.
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 Hey, like some AC/DC songs.
I love AC/DC.
I'm going to call on music.
So what's,
What does AC/DC stand for again?
it's a band, it's,
Well, it's like the some
alternating current, direct current, yeah, yeah. So when, when Cole was my older son, when he was little, one of his favorite things to watch was an AC/DC live concert video that we had. And he loved that song. For those about to rock, he would yell fire, or we salute you. He loved that. But what was really funny was there's a part in one of the songs where Angus Young, the guitar player, right? You know who he is? He comes up and he looks at the crowd and he goes like this and he makes like little devil horns at the crowd, like, everybody laughs. So one of our priests at church, Father Joe, he likes AC/DC too. And so we had told Cole, when you see Father Joe, you want to give him a little devil horns next time, like just for fun. So so it was communion. And Cole was like 3 and he goes up to the altar rail and he's not taking communion yet, but he's there to get a blessing, right? So he's sitting there at the altar, kneeling at the altar rail like this. Father Joe comes by and he goes like this to give him a blessing and Cole goes. Father Joe just turned around. He was laughing so hard he couldn't even finish what he was doing. He was like, I can't believe this little child just made devil horns at the altar rail. I'm done. It's amusing. It was very amusing. He still laughs about it. He's like, remember that time your kid made, I'm like, yep, I do. And they're still friends. Actually, Joe was Cole's confirmation sponsor when he did confirmation. They're still really good friends, even to this day, years later. But yeah, that was amusing. Devil horns at the altar rail.
Daddy,
Yeah,
so you need to bring a internet cable device or you don't need to?
it's bet if you have one today, or at
Yeah,
least
have
at
one.
least 1 or 2 people on your team have one today, you'll be good. Because today's lab is like it's a research, it's a research lab, and you're gonna be going online.
Interesting. Well, we have some chill labs since for a bit we've only had a bunch of crazy labs.
Yeah. So this one will be a research lab. Then we have where we make our own bouncy balls. That's a fun lab. Then we're gonna have we have a DNA RNA game. It's a game you guys are gonna play. And it's kind of like a puzzle game. That one's fun. Yeah.
So far, it's hardest lessons to like,
Oh yeah.
learn.
In our last
Sounds like-
lab, we're gonna extract our own DNA so you can see your own DNA.
What?
Mhm.
To see who our real parents are.
Yeah. That's funny. You're not gonna analyze it. You're just gonna visualize it. You're gonna be able to see it, but you're not gonna be able to analyze it. But next year we are. Next year, we're gonna take a DNA sample and we're gonna run it through electrophoresis and create a DNA fingerprint. Into your mouth. You don't have to stick, we don't have to stick anybody. Nobody's drawing blood or anything. Yeah, it's just your mouth. Epithelial cells in your, when they do it, like when they get samples from people, they call it a buccal swab. They wipe the inside of your mouth with the swab. But we're not doing a buccal swab. You're gonna actually swish. It's like salt water. You have to swish it around in your mouth. Yeah, it's really salty. It tastes gross, really gross. But it's fun. It's really a fun lab. It's cool.
I don't want here to be.
Oh, everybody's gonna do it.
No.
Yes, it's fun. Everybody will do it.
My lunch is gonna be wrong.
Nah, you'll be fine. I do have, Your mom was like, whoops, I was supposed to send them with a device. I forgot. I'm like, it's fine, there will be enough. No, their mom.
Never lets me bring a device.
It's fine. As long as there's a couple within your team, you'll be fine. Because people can like research different things at different times, or you can work on it all together. The trick's going to be just that you keep working efficiently the whole time. You just got to keep moving because you got a limited amount of time. And then, so I'm going to put that out in this week's email. I don't think we're going to be able to do it this spring. We're going to do it in the fall. You can still come. You can still come. You'll be on the email list, so you'll know about it. Because the problem was they changed.
What day is it?
I don't have a date yet. They
Well,
changed the
it
way,
said that it said like it's around May 9th.
right, but it fell through. So they changed the process for reserving the venue. And I followed the new process, but there was one thing I didn't properly click, which wasn't something, it was a time frame. In the past, you never had to select a time frame. A rental is a day-long rental. A rental is still a day-long rental, but apparently I didn't click the time thing, which allowed like the automated system to let somebody else come in and reserve another block during the day. And they ended up giving it to that person instead of us. So I asked around about May 30, but that's like Memorial Day week and a lot of people are gone, and I didn't get enough people who committed and said they could do it. So I was like, okay, we're gonna move it to the fall. I would like to do it, but I don't see a way to make it work, so I'm a little bummed, but that's okay. Y'all can all still come in the fall. It'll be good. All right.
Wait, what?
Oh, the dance. I'm not gonna be able to make it work. I'm annoyed, believe me. Nobody's as annoyed as I am, because oh, all right, she's making an outfit. Oh, all right.
White shirt with one of these neck things.
Okay, yeah.
And then one of those pants that are like piece here,
Yeah, yeah.
piece here, and then suspenders.
We will make it work. Don't worry, we'll get it done. It's gonna be late because there's just no way to make it go. I've tried.
Here in the fall,
Oh, why?
I might be moving,
Oh, really? Okay.
maybe to the Netherlands.
Moving to the Netherlands?
What?
Really? Your dad got a job there or something, or?
He's working on getting a job, but we might just go up and moving to find a job with.
Well,
him there.
I've been to the Netherlands and I loved it. It's an absolutely beautiful place. So if you do go, you will enjoy it. Not too bad. I mean, I don't know. I was there not when it was snowing, but I mean, I suppose it does snow. It's just really cool because like a lot of the if you go to Amsterdam, there's waterways where there would be streets in some places. It's really kind of cool. What where there? I wasn't there when it snowed. We weren't there during snowy season. Oh, here? What did I do when it snowed? Played outside a little bit and then mostly just watched it.
I had a snowball fight with my friend.
All right, well, let's get started. Again, I still have a little bit of a cough. It's just this allergy lingering business. It's just my little cough reflex is triggered and nothing's gonna make it stop unless I take steroids, and I try not to take them because when I need them to work, I need them to work. All right, so today we are starting a new unit, and this is our nuclear and organic chemistry unit. So today is our only little bit. We're going to talk about nuclear chemistry. We don't spend a whole lot of time on it. We move on to organic chemistry after this because next year in biology, that's kind of the background we need. So we kind of prep ourselves for that. So today we're learning about atomic nuclei, nuclear stability, nuclear change, and uses of nuclear chemistry. Oh, you'll learn. So atomic nuclei and nuclear stability. All right, so we have strong nuclear force. Now, way back at the beginning of the year, we talked about strong and weak nuclear force. So your strong nuclear force is that the nucleus of an atom occupies a tiny fraction of the volume of the atom. And what do you find in the nucleus, Annabelle?
The number of electrons.
In the nucleus? Not electrons. What else is there?
Protons.
Protons and what, Emerson? Protons and neutrons. Very good. That is characteristic of a given isotope. Do you remember what an isotope is?
Is a atom with a different number of neutrons?
Yes, an atom with a different number of neutrons, which means its mass is different from its optimal state. They are. Neutrons have the most mass. Right. Okay. So electrostatic repulsions would normally cause the positively charged protons to repel each other, but the nucleus doesn't fly apart because of the strong nuclear force, which is extremely powerful but short-range attractive force between nucleons. So if you have two magnets and you have the positive poles and you try and push them together, they repel each other, right? Yeah, you can make them, but you got to use force because they're pushing.
Okay.
And that's how like maglev trains work and all kinds of technology uses that. So there are nucleons in there, and we also have things called gluons in there, but that's what keeps it from just flying apart, because otherwise it would. All stable nuclei except hydrogen contain at least one what?
Electron?
There you go. Neutron. Remember, hydrogen doesn't have a neutron. It just has an electron and a proton, and that's it. But you're on the right track. So has at least one neutron to overcome the electrostatic repulsion between the protons. So the neutrons are there to keep the protons from pushing pushing away from each other and making the whole nucleus just go boom and explode.
So the neutrons weren't there, it would explode.
Yeah, they get in between and they keep those positive particles from pushing each other apart, okay? As the number of protons in the nucleus increases, the number of neutrons needed for a stable nucleus increases even more rapidly. Too many protons or too few neutrons in the nucleus is a result of an imbalance in the forces, which leads to what we call nuclear instability. All right, so we have something called a mass defect. So the mass defect is the difference between the mass of the atom and the sum of the masses of the atoms, protons, neutrons, and electrons. And call that the
Individual parts.
yeah, those are the individual, we call that the mass defect. So it's the mass that is converted to energy when the nucleons form a nucleus. Okay, so if you were to take all the individual parts, so in this case, let's say, okay, the purple is our electrons, let's say the green is the neutrons, and the light blue is the protons. And if you were to add up the individual masses, you would get this number right here. But the actual mass when they're all combined is less because some of the mass is converted to energy when the nucleus is formed. Because remember, mass doesn't go away, it changes form. And in this case, mass gets converted to energy. And that's kind of a new concept for you guys, right? We haven't talked about mass getting converted to energy, but it does. And this is an example of when. So it's called nuclear binding energy.
So the thing you mentioned before is called nuclear binding.
Yes. Nuclear reactions, like chemical reactions, are accompanied by changes in what? What do you think? Nuclear reactions, like chemical reactions, changes in energy. Oh, sorry, your hand went up just as I clicked. So
I'm just needing to say.
Yeah.
The word nucleus, for some reason, to me, sounds like a sciencey term for a male private body.
Okay. So here's something though, I'll tell you if you want to get disowned by me. So remember that anytime we're talking about nuclear power, nuclear energy, nuclear weapons, it's because it has to do with the nucleus, right? Do not be somebody who says nuclear power, nuclear energy, nuclear. Don't say nuclear. It's not nuclear. It's nuclear, right? Because it has to do with the nucleus, right? We had a president who said nuclear all the time, and it made me want to jump through the TV. George W. Bush did it. He could not say the word nuclear to save his life. He said nuclear. And I'm like, somebody in one of your handlers should fix you because you sound like a moron. So it is nuclear, right? Not nuclear, not nuclear. Nuclear, not nuclear. All right. The energy changes in nuclear reactions, however, are enormous compared with those of much energetic and chemical reactions.
I'm saying nuclear.
Mm-hmm. Yes.
Say new.
Clear.
Say
Yep.
clear.
The nucleus, it's not the nucleus, it's a nucleus, right? So in fact, energy changes in a typical nuclear reaction are so large that they result in a measurable change in mass. So in this section of this lesson, we're describing the relationship between mass and energy, nuclear reactions, and show how energy in nuclear reactions and show how the seemingly small changes in mass that accompany nuclear reactions result in the release of enormous amounts of energy. And here's where Einstein comes in. So we talk about mass getting converted to energy being kind of a new concept to you guys. Einstein had a famous equation right there that deals with, yes, it deals with the relationship between mass and energy. Einstein figured it out. It's E equals mc squared. Now you want to know something funny? My doctor, his name is Alan Einstein. That's his name. And he is distantly related, but he plays on it all the time. His concierge service is called Einstein Genius Care. It used to be called EMC2 Care. Like he plays on this all the time. You go in his office and the wallpaper is covered in Einstein's equations. Like he's all about it. So this is the equation. E equals MC squared. Have you heard this before?
Yeah.
Yeah, it's a
Definitely.
famous equation, right? So what does it mean? Do you know what the C stands for?
C is the.
This is wild. Okay, the C is for the speed of light, which is 2.998 times 10 to the, it's 108 meters per second square. It's really, really fast, right? And
C instead of S is already chosen.
S is for lots of things. So he used C. And then E, what do you think E means?
Energy. mass.
Energy, right? And in joules. Yeah,
And
very
that
good.
is in,
What's mass going to be measured in, do you think? Do you know?
Mass is kilos. or
Okay,
kilojoules.
kilograms, right? Kilograms. So he's using the speed of light, mass in joule, I'm sorry, energy in joules and mass in kilograms. And that's how he explains the relationship between mass and energy. So it can be done. All right, so nuclear change. What's nuclear change? All right, well, we have what's called a band of stability. An atom is stable if the forces among the particles that make up the nucleus are balanced. An atom is unstable. And what do we call an unstable atom? What's the word for it? Annabelle, do you know?
Radioactive.
Radioactive. If these forces are unbalanced, the nucleus has an excess of internal energy. Instability of an atom's nucleus may result from an excess of either neutrons or protons. I might have to adjust volume here. Let's see. I haven't done that yet today to check it. It's not too bad.
What you might not know is performance and durability go right along with it.
Yep, great. Okay.
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of 2 neutrons and 2 protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron, either through alpha, beta minus, or beta plus decay.
So when you look right there at that, whoops, go away. So you can actually have a neutron in beta minus decay that changes into a proton and electron, and the electron gets lost. And you can also have a proton that changes into a neutron and a positron, which is like an electron, but instead of being negatively charged, it's positively charged. So the particles themselves are changing, and change requires energy, either coming in or going out of the system. So that's where we get the radioactive decay. Okay, so next page. Okay, so nuclear change. So what causes this change? The belt of stability, this is what he was just talking about, makes it easy to determine where the alpha decay, beta decay, and positron emission or electron capture will occur. Alpha decay, which is it can be abbreviated with this AA. Alpha decay is located to the where of the line? Yeah. Yep, it's at the top, right at the top of the line, because the alpha decay decreases the mass number of the element to keep the isotope stable. This is accomplished by emitting an alpha particle, which is just a what? What's an alpha particle? What is it?
Particle that is that.
Basically, remember it said it was 2 protons and 2 neutrons? So you know what it basically is? It's basically like it's helium. Yeah, it's basically like it's emitting helium in the nucleus. So in this decay pathway, an unstable isotope's proton number is decreased by 2. So basically what you guys need to what I want y'all to understand is that these particles are changing. That's releasing or gaining energy in these systems. Anytime something changes, something needs to happen to a system, right? The energy has to go in or out. But particles are changing. Emerson, give her some space, honey. The particles are changing. You've got changes in energy. That's the radioactivity. But here's the thing. Remember, what determines what type of element an atom is? What's the thing? The actual thing. You can have a different number of electrons, and it's an ion. You can have a different number of neutrons, and it's an isotope. But what has to be? Protons. The number of protons determines what element it is. So if you have a decay that changes the number of protons, you have now changed the whole element. It is now something entirely different. And that is what we use for radiocarbon dating and things like that, which we're going to talk about in a minute. So keep in mind that they're changing particles, which the end result is a new element is formed, a completely different element. You good back there, Lucy? So beta decay accepts a proton, so it changes the amount of protons and neutrons. The number of protons increase by 1 and the neutron number decreases by 1. And then lastly, you have this positron decay, which is where you get the little protons and the little positrons, which are the little plus charged particles, kind of like electrons, but plus charged. As with all decay pathways, if the daughter nuclides, which is what is formed, they call it the daughter nuclides, it's a parent and daughter. That's what they call them. So they are not in the belt. If they're not on this belt one way or another, then that's how you can tell what kind of decay it is. Right, right. Okay, so let's talk about fission for a minute. In nuclear physics, in nuclear chemistry, nuclear fission is a nuclear reaction or radioactive decay process in which the nucleus of an atom splits into two or more smaller, lighter nuclei. Okay, we're not talking about changing particles now. We're talking about splitting a nucleus. All right, so
Nucleus is like, it's like nucleus, but
nuclei is plural for
Yeah.
nucleus. Yep. So nuclear fission is the subdivision of a heavy atomic nucleus, such as uranium or plutonium. Most of these nuclear reactions that we manage as humans involve the very heavy elements, the ones with the highest mass.
There was an analog for related to uranium.
Uh-huh.
Where people were eating uranium
Oh.
fungi and it was turning them strange.
I wouldn't want to do that. So such as uranium or plutonium into fragments of roughly equal mass. The process accompanied by the release of, what do you think is going to happen? A large amount of what's going to get released if you split a nucleus? Radioactivity, but specifically
Split causing
big release of what?
nucleus.
Energy, a huge amount of energy. So you're talking about a tiny nucleus. You split one tiny nucleus, you know what you get? You ever heard of the atomic bomb?
Yep.
That much energy. Yeah, that much energy, a lot of energy. Fission occurs when a neutron slams into a larger atom, forcing it to excite and split into two smaller atoms, known as fission products. Additional neutrons are also released that can indicate a chain reaction. So that's what happens. You split one, and then they start a chain reaction, and it splits a lot of others. So when each atom splits, a tremendous amount of energy is released. Uranium and plutonium are most commonly used for fission reactions in nuclear power reactors because they are easy to initiate and control because they're so massive. Energy released by fission in these reactions heats water into steam, and the steam is used to spin a carbine, and it produces carbon-free electricity. Nuclear power is the cleanest form, one of the cleanest forms of energy. Now, it does produce waste products that are radioactive, and then you have to deal with them. But there are ways to deal with those products. But if you're splitting atoms in a controlled way, you can produce a lot of power, a lot of power. So there is definitely a push to increase our nuclear power capability, but you need a lot of water to cool the reactors. But that heated water is then used to spin a turbine, and spinning the turbine is what's used to produce electricity, power, right? It's converting that energy of motion, kinetic energy, into electrical energy, and then it goes through your wires to your house. But if you've ever seen a nuclear power plant, and there are some that are not too far from here, you may have seen them on a drive, they have these big towers, and there's steam coming out of them all the time. So that's what you get. You have one atom that gets split, and then it causes a chain reaction, and a bunch of atoms split. So fission versus fusion. Fission is when you split an atom, the nucleus of an atom. Fusion is when you force them to combine. Do you remember we talked about particle accelerators a while back?
It's like synthesis and decomposition.
Kind of, yeah. Remember we talked about particle accelerators where they're taking very heavy nuclei and they're spinning them around in this centrifuge, basically, like really fast till they smack into each other and combine, and they will combine for like a fraction of a second, and we're like, new element, but it's not stable, but we did it, you know, for just a minute. So that's kind of the idea. So here are some fuel types. For example, you have uranium and plutonium, and then over here, you've got hydrogen. So this is fusion. This is fission. Notice for fission, we're using heavy, massive elements, right? But for fusion, we're using the lightest, the least massive element. That makes sense, right? You want to split the bigger thing, and you want to combine the smaller things. So we use nuclear fuel is created from plutonium, it's usually electricity. And when you combine two hydrogen together, you get a helium. If you combine two hydrogen nuclei, you get helium. So we're still working on controlling this. Okay, we have some like hydrogen fuel cell stuff that we've done, but we're still working on making it useful for the general public, right? And we use nuclear power regularly. And if you look here, nuclear power is 1,000,000 times greater than other energy sources. But hydrogen fusion, when we master it, will be 3 to 4 times greater than fusion. And then fission, which is 1,000,000 times greater. So you're talking 3 to 4 million times greater than what we do. Okay, if you can make something twice as good, that's great. 3 to 4 million times is huge. So this is the technology we're working on now. So how does the sun make energy? This is how the sun does it. The sun does a fission fusion situation. That's what that is. Sorry.
This season, get the fun started with the right stuff at the right price. For a limited time, save 25.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to be close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
With gravity crushing things down, things get close enough together and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, they bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second, every day, about 5 million tons of stuff is being converted to energy. It's amazing.
So that's where we get our energy from the sun, right? All right, so nuclear change, a little more on nuclear change. The chain reaction, this is like dominoes, right? So a chain reaction refers to a process in which neutrons released in fission produce an additional fission in at least one other nucleus. This nucleus in turn produces neutrons and repeats the process. So here's an example in the little image here. Here it goes, dink, 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 right? Okay, chain reaction, that's what we get. To maintain a controlled nuclear reaction, for every 2 or 3 neutrons released, only one must be allowed to strike another uranium nucleus. If this ratio is less than 1, then the reaction will die out. And if it's greater than 1, it becomes uncontrolled and you get an atomic explosion, which is not good unless that's what you're trying to do, I guess. So let's look at this here. This, I think, is in your notes. What do we have for number 1? What do you have, Annabelle?
Gamma ray.
Gamma decay. Very good. What do we have for number 2? Alpha decay. How about number 3? Who's got 3? Emerson? Beta decay. All right. Scientists use the amount of radioactive isotopes found in rocks and fossils to calculate the age of rocks and fossils, and it's called what? Annabelle?
Radioactive dating.
Radioactive dating. Yes.
So it says 3% decay is beta plus and beta minus. Why is there gamma decay?
It's that's a good question. Let me get back to you. I'm not sure why it's labeled differently. So let me look it up during lab and I'll let you know, because that's a good question. I'm not positive why it did it that way. All right, what consists of 2 protons and 2 neutrons that is positively charged? What's that? Alpha particle. And what involves particles found in the nucleus of an atom and it changes one element into another element? What's that? You do a nuclear reaction. Yeah. All right. And then what consists of high energy waves is always accompanies alpha and beta decay? Annabelle? Gamma radiation. Yep. And the spontaneous emission of radiation by an unstable atomic nucleus. What do we call that? Do you have it, Emerson? Or Everly? Do you guys have number 8? Either of you? You're looking? What you got? Just looking. Annabelle, do you have it?
Radioactivity.
Radioactivity. All right, Everly, why don't you look at number 10 for me? How about number 9? Can be followed through the steps of a chemical reaction or industrial process. What's this one? Number 9. What'd you get, Eunice?
A tracer.
A tracer. Yeah, it's something you use to follow the steps. Do you have number 10, Everly? Do you know? You want to give it a guess? Fast moving electron given off by a nucleus. Do we know? It's going to be a beta particle. All right. And then how about half the radioactive atoms in a sample of sodium-24 will decay in 15 hours. 15 hours is what? What do we call it? A half-life. So let's talk about that. How do we use nuclear chemistry? Well, we use it when we're dealing with this half-life situation. An interesting and useful aspect of radioactive decay is a half-life, which is the amount of time it takes for 1/2 of the radioactive isotope to decay. The half-life of a specific radioactive isotope is constant, it's unaffected by conditions, and it's independent of the initial amount of isotope. So if you've watched Harry Potter, you know when they see Voldemort drinking the unicorn blood, they say, you've slain something so pure and defenseless to save yourself, you will have but a half-life, a cursed life from the moment the blood touches your lips, a half-life. And then a few years back, they had this unicorn frappuccino at Starbucks. So there was a joke that everybody was drinking, the unicorn blood and they were going to have a half-life. So we use radiocarbon dating. We take that half-life that we know, it's a standard, it's a number we know, and it's a method that provides objective age estimates for carbon-based materials that originated from living things, the amount of carbon-14 present in a sample, and comparing this against internationally used reference standard. This is why this is important. So you can age a fossil objectively or subjectively. So if you are looking at, say, layers of rock or other fossils that are in the same layer, you can guesstimate how old a fossil is. It's an estimate, but it's more of a guess. If you're estimating, right? You're estimating this fossil is 250 million years old because it's in a layer of rock that you know was in this area 250 million years ago. Or you see a shell and it's beside another shell, and you know that this organism lived 250 million years ago, and since they're side by side, this one must have lived 250 million years ago. You can date that way, but you can also date with radiocarbon dating, and it's exact. It is objective. It has nothing to do with what's going on around it. Yeah.
Or you could date by asking someone to go out.
That's a good one. So what happens is this log, okay, when this log is brand new and it dies, this tree branch dies, it's going to have 100% of the carbon-14 that it started out with. But at 5,730 years, it's only going to have half of the carbon-14 that it started with. Yeah, and in 11,460 years, it's only going to have a quarter of the carbon-14 that it started with. And 17,190 years, it's only going to have 12.5. It halves. And we know the exact number of years. And because of that, we can date things exactly. So here's a quick video on this. How does radiocarbon dating work?
Please tell me there's a meme of two things.
Hit.
At Wayfair, we get pretty excited about.
Oh, no, we got a Wayfair commercial though. Yeah. Kelly Clarkson. Thanks, Kelly.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants want carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
So we use carbon for stuff that's not quite as old, but then we can use radio dating for other elements that are heavier, and we can find out even more. So another use of nuclear chemistry, practical applications of radioactive isotopes. Okay, well look, these are all different radioactive isotopes and different ways they can be used. Everything from electroplating, which we talked about last week, to research in red blood cell survival studies, to medical diagnoses, to sterilizing surgical instruments, analyzing metal alloys. These are all ways we can use radioactive isotopes. There's even more. It keeps going. Look at all the different ways. Now, uranium and plutonium, remember it said those are used often in power, but plutonium, it says there it's powered more than 20 NASA spacecraft since 1972. And we've got 2 uraniums here. So uranium-234 is used in dental fixtures like crowns, but uranium-235 is what we use in power plants. And then we have a xenon here, used for lung ventilation, blood flow studies. Look at all these things. Sulfur, genetics and microbiology research. Thorium. We have all kinds of cool options here. Helps fluorescent lights last longer. We use lots of radioactive isotopes. You girls okay? Hang on with me for just this little bit. I know it's just dust and the light's hitting it perfectly. So number 1, radioactive isotopes can be followed through a series of steps, of a chemical reaction or industrial process. And what do we call these? Eunice. Tracers. Okay, this is important. So all right, pay attention, girls. This is important. So sometimes there are tracers that we use in medical processes or in chemical reactions or in industrial processes, but it allows you to follow the steps, which is important if you're trying to perfect a pathway or work a certain treatment or something like that. How about number 2, which statement is not true of radioactive decay? It involves the nucleus of an atom. It involves radioactive isotopes. The identity of the atom remains the same, or fast-moving particles and energy are released. What do we think? C? Yeah, it's C, because remember I said you actually change the element because the number of protons changes. So that means the element actually changes. All right, and then alpha and beta decay are almost always accompanied by what? What you get, Annabelle? For number 3. Do you know? Do you know, Eunice?
If we're using atomic number.
It's gamma radiation. And I'm gonna come back to that one again, I told you. So in relation to the original atom, the atom that results from beta decay has an atomic number that's what? Do we know? No? Number 4?
Stays the same.
It's gonna be 1 more. Because it's got an atomic number that's gonna be 1 more. So what does that mean that it's gained?
It's gained a neutron.
No, if you're gonna change your atomic number, you're gonna become a new element, a proton. Very good, you got it. All right, so here's what I want you to do. Listen, you've got like 4 minutes, but what I want you to do for the next 4 minutes is I want you to get out your devices if they're not already online. Take a minute and whoops, are there. Be sure that you're online with whatever devices you have, if you have them. Put away your binders and get your pencil out so that you'll be ready for lab.
So go to the site, lab rats.